Thank you for the kind introduction. As mentioned, I'm Milan. I'm a PhD student in Marco Pavone's lab, and I'll be talking about a series of works, all centered around the idea of embodied reasoning to help with auto-distribution reliability on autonomy. So a lot of the works will be around this notion of vision language action models that have been repeatedly discussed in the past the past presentations, but I'll give a quick primer. So VLAs are a very recent end-to-end robotics learning model paradigm and are very powerful generalist policies. They've been introduced in various domains, including manipulation, such as the RT2, and pi models, as well as in autonomous driving. For instance, 2 years back, Waymo came out with the EMMA paradigm, and recently NVIDIA came out with AlphaMeo 1.5. And so what are vision language action models? VLAs essentially leverage internet scale data in the form of visual and semantic priors from vision language models such as Gemini, Qwen, so on and so forth. And with these multimodal models, you continue training them on relatively limited amounts of robotics data. This could be, for instance, in manipulation, the bridge data set or Joy data set, or for autonomous driving, new scenes, and so on. And this imbues the vision language model with action knowledge or action prediction knowledge. And so finally, you get your end product, which is the vision language action model, in which it takes in as input the image of the scene, as well as a task instruction. It could take in other modalities, but these are the two that we'll focus right now, and will output actions that are executable controls. Now, there's various variants of this with different architectures, action heads, and so on, but this is the general paradigm and recipe. So recently, there has been this shift, or at least this new step forward into augmenting this design with chain of thought reasoning, which is intermediate action relevant, or hopefully action relevant information in the form of text, mostly text, but there are examples of other modalities, but today I'll be focusing on text. And these can include things like meta action, which is like move left or steer right, or visible objects, which are bounding boxes and so on, or ego states, like the position of the end effector for manipulation, or your position on the road for navigation. So you train them all to output all of these intermediate steps before outputting your actions. And so this is very similar to the chain of thought reasoning in language modeling or vision language VQA analysis. And so therefore, that's inherited this name of embodied chain of thought. So why is this augmentation of embodied reasoning so useful? So at the beginning of VLAs, there's been this observation that adding auxiliary signals, which are other losses beyond just action predictive signals, improve VLA performance. And this has been noticed in works such as AlphaMeo, which I'm sure you're familiar with. But reasoning in text has quite some benefits, including human interpretability. So you can actually read it and you can analyze it, especially in failure situations, and also provides rich training signal as auxiliary objectives that you can perhaps train with process rewards or co-train. So given this background, I want to address roughly 3 broad questions, or at least take a step forward in these 3 questions about embodied reasoning. So one is, what should we be reasoning about? Like, what is good reasoning, and how do we discover what good reasoning looks like? The second is, how should we reason, specifically in failure instances, in a real-time manner that considers latency and so on and so forth. And then third is, when should we reason, or specifically, how and when should we allocate reasoning as a general form of test time compute? So let's dive into the first direction, which is what should we be reasoning about? This is a recent work that will be presented in RSS 2026, titled Self-Supervised Bootstrapping of Action Predictive Embodied Reasoning. And so essentially, we treat reasoning as a latent variable to discover embodiment alliance strategies without the use of external rewards or human labels or so on and so forth. So I want to discuss two problems in understanding what makes good embodied reasoning. One is the grounding problem, namely that there's not too much data that grounds physical actions with reasoning, right? We're just putting two things together and we think this particular type of reasoning is useful or hopefully helpful in predicting your actions, but we don't know for sure. We don't have a ground truth knowledge of this, and there's no obvious way to validate good reasoning. So you end up with this chicken and egg problem where to ground reasoning in the physical world, we need a source of labeled reasoning data. But to validate and generate reasoning data, you need a physically grounded model. So that was problem A. Problem B, or related problem, is about verbosity. So as I just mentioned, intermediate reasoning includes, for instance, these are examples: plan or visible objects, pedestrians in the scene, or gripper position or end effector, or also your position on the road and so on. But is planning at every step necessary, or is it verbose? Is analyzing all perception features, all bounding boxes important, or could that be distracting? And gripper position or your position on the road, is that actually informative in predicting your action, or will it actually degrade your performance? So these are all questions we want to answer under this broad central research question, which is, what does embodiment aligned reasoning look like? So more nuanced is, how do we refine and align internet scale vision and semantic priors, because foundation models and human label annotations can generate synthetic data, which is perhaps useful, but we want to see what's useful in embodiment specific robotics reasoning skills, and has to be in a self-supervised manner. At least is how we envision it, because you have to enter into that sort of chicken and egg loop. So to this end, I propose the work we've been doing, R&B Encore, which is short for Refine and Bootstrap Embodiment-Specific Chain of Thought Reasoning. And so the insight in here is we treat reasoning as an unobserved latent variable for observed context and actions, and we leverage variational inference priors, or variational inference tools, to leverage these priors. And so, as you can see, there's a probabilistic graphical model, and the observed variables is the data you actually know of, or at least train on, which is image, task, and actions, and you want to discover that intermediate good reasoning trace. So I won't go into too much of the mathematical details, that's reserved for the paper, but at a high level, our approach is based on a specific variational inference technique called importance-weighted autoencoders, which we adapt. And basically, we take in the observed data, which is the context and action, into a model called what we are terming as a reasoning proposer, which generates hypothetical reasoning traces that might be useful, but we want to figure it out. And the way we figure it out is we have a reasoning validator, which is a score based on, again, variational inference objectives, the goal being the scoring being based on concision of the reasoning. You don't want long traces, action predictability, so you ground. That's how you get the grounding in physical space, and non-triviality, which is a notion of generalization. And then with that, you choose your best reasoning, and that's used as your ultimate good reasoning data. So using this technique, we can analyze good reasoning for various types of embodiments. So we looked at manipulation, legged locomotion and navigation, and self-driving navigation. And so I'll quickly describe, for instance, in manipulation, we discover a new reasoning distribution where, and this is going to be a repeated motif, that meta actions, which is short descriptions of where you want to move, like move left, move right, or move, drive forward. This is a very useful, very predictive, action predictive type of reasoning, which is a confirmation of some of the hints from past papers, including RT2 and Alpamea. Another thing that we notice is, at least in simulation, visible objects were pruned, which we'll get to later, but list of bounding boxes in simulation appear to be less important. Overall, we see improved performance with our reasoning and shorter reasoning traces because we're pruning less important information. So getting a bit of a deep dive on the visible objects list. So the fact that visible objects was pruned doesn't necessarily mean perception is not useful reasoning. So one of my colleagues, Katie Lowe, has his background on bounding boxes for autonomous vehicles. And so we decided to look deeper into what is maybe list of all the bounding boxes as useless, but maybe particular objects are useful to attend to. And so we treat the list of bounding boxes itself as a latent variable. Using our technique, we can figure out essentially what are task salient features by a three-fold order magnitude increase over listing all objects, meaning that our reasoning or perception reasoning is more distraction-free compared to other forms of general throwing every single bounding box in the same type of reasoning. We improve performance, and ultimately this is a way to prune out distractions and irrelevant objects and get the most relevant action task salient objects. We try our approach on physical hardware for manipulation. We see improved performance, especially in auto-distribution tasks, like those with a lot of visual clutter or auto-distribution targets. Seeing similar types of trends with simulation. We also looked into legged locomotion. So it's another form of navigation. In this case, the synthetic data, the proposed recent data comes from the base VLM itself. And so this is an important paradigm. I think this is, I was very excited about this result, which is that we can show self-improving embodied reasoning models where a VLM proposes hypothetical reasoning traces and then uses our approach to refine and bootstrap performance in a very positive feedback cycle. So we look into various types of navigation or embodiments like quadruped, bipedal, bike and wheeled robot, thanks to the Navitrace data set. Just a quick takeaway from this one is that in legged locomotion, one of the most useful types of reasoning is affordances, which is how external structures provide capabilities to the eco agent. So in this instance over here, if you reason about everything, like in all primitives, you get distracted, you end up in the ice. The glacier, on the left, you see the ideal trajectory, and then all primitives reasons about everything, and you end up in the ice, and so that's not good. Random primitives, which is just a random set of the types of reasoning, doesn't explicitly reason about affordances, and so we attributed that to why it's also spending a lot of time on the ice. But our approach is able to maintain most of its trajectory on the ground truth path, which it discovers, but also minimal contact with the ice because it explicitly reasons about obstacles and affordances. And then we also try our approach for autonomous vehicles, specifically on the new scenes data set. And the reasoning here was generated by human annotations. And so again, we see meta actions are very useful, as well as visible objects, whereas there's a lower emphasis on hallucinated experiences. And overall, we predictably see with our approach reduction in path error and collision rates. So takeaways for this is selective reasoning is very important and much more useful than exhaustive reasoning because we're able to curate which reasoning types and primitives a VLA model actually finds useful. Second is self-supervised bootstrapping works, which is a way to enter again into that chicken and egg problem of the source of data and source of model. And so our approach is able to take large-scale internet-scale priors from VLMs and distill that into useful reasoning. Without external rewards, verifiers, and human annotations to guide this process. And we also show generalization across embodiments and scales from manipulation, navigation, driving on 1B all the way to 30B model sizes. The second, so we talk about what is good reasoning, and we have a paradigm for that. Second is how should we reason, or specifically in failure situations. And so this is work that I presented in Coral last year. And so autonomous systems, we know, are expanding their deployment regions from structured, localized settings to more unstructured settings. Think of Waymo and all the other companies. But in the process, they can experience out-of-distribution failures, which can lead to damage to hardware, endanger human users, environmental hazards, and so on. The traditional technique, which traditional being using foundation models in the past couple of years, has been leveraging these language and vision language models naively to understand out-of-distribution scenes and perform high-level response reasoning. So, land at a location, but not actually implement that in a zero-shot manner. But So these are the good parts of foundation models. The cons about these approaches is that they're limited to localized repairs. The fallback responses are hard-coded and require human interventions. And just querying, if you query any of these models, they do take quite some time. And so you incur high latency. So how do we respond to out-of-distribution failure situations? In this paper, we identified three core components to this. One is identifying a fallback strategy. Second is adaptively detecting unsafe regions or semantically or conceptually unsafe regions like high temperature or near a human and so on. And then swiftly generating safe fallback plans at the safety critical moment. And so I'll introduce our approach called Fortress, out-of-distribution failure prevention in real time by generating and reasoning about fallback strategies. So it's a hierarchical approach where at a slow frequency, we do reasoning about safety and goals. And at the safety critical moment, we combine all that information together and rapidly generate fallback plans. So one component is identifying fallback goals. This is done at a low frequency once every 10 seconds, where an LLM or a human can, outline at a high level what are some things that might be useful. So like in language form, like land on rooftops, land on empty park for a drone, or pull to the road shoulder for autonomous driving. We feed these into a vision language model, such as Molmo, which can actually point to things. And now there's more models in the past year that have been developed since the publication of this paper. And so essentially, these will point to 2D coordinates. We can convert them into 3D coordinates with depth sensing. And then we cache these full coordinates every 10 seconds. And these will be used later on. The second component is semantic safety, which is this notion of conceptually, regions in space that are unsafe. And so we query a, vision language models such as Gemini or whatnot to give high-level terse descriptions of failure modes. So like it will say, in this type of scene with this embodiment, you might have worker injury, sharp objects, cable entanglement. We extract that, this sort of reasoning of what are high-level descriptions of failure modes and embed them. So you have embedding, failure embeddings of potential things that might go wrong. And then you might have collected a lot of safe data. You might not have a lot of failure data per se, but a lot of safe data. So what should scenes look like? And you might have descriptions in semantic form in the form of logs. And we found you can use 10 minutes of collected data, and this would work at least on quadruped navigation. And so you would embed and have a database of safe embeddings. To save you from all the math, this is conformal prediction, which is essentially creating cost function thresholds saying, is new data streaming in abnormally close to a failure mode compared to all the safe data? So maybe you have a failure mode of high temperature. If you see something on fire, it identifies fire. There's an out of distribution situation. You would use our conformal prediction threshold to see in textual embedding space whether that description is abnormally close to the embedding of high temperature compared to all the safe data that you've seen. So that's how our semantic safety embedding cost functions work. They're very quick to query, so that at the safety critical moment, when a failure detector has triggered the need for a fallback response, you can detect all the objects in space and pass it through our embedding cost function. And you can identify, at a particular region, there's a worker injury hazard because there's a person on a ladder. So you need to steer clear from it. Whereas there's a ladder, just a normal ladder on the ground. And so that's simple object avoidance. And so at the safety critical moment, when you want a fallback plan, you solve a reach avoid problem where you reach a particular goal using a VLM and perform worst case analysis of failure modes using our embedding cost function and slide it into the planner. And essentially you can slide our embedding cost function into any motion planner and solve this reach avoid problem to obtain rapidly fallback responses. And so here's an example of this where essentially the drone needs to find some fallback strategy and identifies, there's a region under fire, there's a caution region, there's a region where there's cars, so it shouldn't land on those building rooftops, but a rooftop garden, it understands is a pretty safe place. to land. And so to summarize, Fortress is essentially a slow, fast hierarchy for OD failure prevention and can process human describable fallback strategies by anticipating and avoiding conceptual failures. And our approach is control algorithm agnostic. And so you can slide in a learn planner or MPC and RRT and so on. So I realize I don't have too much time remaining, but I do want to talk about our very recent work that's under submission that describes when to reason, specifically direct when and where to allocate test time compute in embodied planners. So very briefly, we're looking at hierarchical planning where a high-level user prompt might be fed into a vision language model that can decompose abstract instructions into executable subskills for embodied agents. And in this paradigm, this subskill is fed to a low-level policy. So it's a system one, system two architecture once again. And that's executed by the low-level policy by orchestrating with the VLM. And so this is a paradigm for hierarchical planning that is pervasive throughout many embodiments. And so with this sort of high-level planning, people are trying to understand ways to improve the performance of these. And so one approach to do this is investing in test time computer cost expenditure during the inference time. And so there's different axes of scaling for this. So one is I've been discussing about chain of thought or reasoning. The other is model size, like how large you want it, as well as memory context. So how much memory or how much context you have. So our investigations show that all these different axes actually produce different forms of gains. And scaling test on compute is not free in robotics. So chain of thought helps under hidden constraints, but in many tasks, instruct or non-thinking ties with thinking far more cheaply. Model size helps broaden skills, but scales erratically, and memory helps history-dependent tasks, but hurts in other cases. So our investigations have three trends. One is there are large capability gaps between cheap and expensive models. Second is the gaps are non-uniform, hinging on task-specific demands like skill command or recall horizon. And three, lightweight models suffice on many tasks. So a static model fixes that latency and capability compromise. So our observation motivate a framework that infers each task demand from the scene context and allocates compute per task accordingly. And so we have this routing framework called Direct, which aims to learn a mapping from the task scene and instruction to the planner best suited to solve it. And so given a user instruction and scene observation, our lightweight router Direct selects the planner with the best quality cost trade-off from a fixed pool of VLM planners. So the chosen VLM decomposes the instruction into primitive subskills executed by the low-level policy, while a transition detector normally used for triggering replanning for multi-stage tasks. And by conditioning on all this multimodal context, we can rapidly, with Direct, allocate test time compute per task, then use a single fixed capability planner. In simulation, our approach achieves the best routing efficiency in every configuration. It recovers or even outperforms the largest and strongest model at lower latency and turns the erratic size scaling curve into the monotonic improvement. So we can help improve test time scaling with the router. And then on hardware, the Franca Droid Direct matches or exceeds a stronger model at up to 65% latency. On multi-step grocery bagging, it reaches 95% success at 7 seconds versus thinking, which is 90% at 20 seconds. So we also find improvements with chain of thought reasoning and memory routing on hardware. So to summarize this quick thing, naively scaling test time compute is wasteful, and our investigations document how different axes of test time compute qualitatively show different capability profiles. And so treating the planner as a dynamic variable enables frontier level embodied planning at a fraction of the cost, while with difficulty inferred from faster compute embedding. So our router is very lightweight. So I presented three different lines of work. What is good reasoning, how to reason in failures, and when to reason in terms of allocating test time compute to improve scaling. And so ultimately, embodied reasoning is a resource that should be discovered, deployed, and budgeted, not a fixed template applied uniformly. I'd like to thank all my collaborators. Obviously, research is a collaborative experience, and so I'd like to thank my advisors, Marco Pavoni and Clark Barrett. And I'm ready for any questions.